Good afternoon, students. I'm Dr. Abdul Hamid. I'm going to take this elective paper A. So today we will see the techniques and measurements. What we'll see. So today we are going to be see about this measurement of Hall voltage from Hall effect. We'll see, and we'll see about the how the Hall voltage can be determined experimentally. That we are going to be see, as well as the we'll see the transmission electron microscope, about the transmission electron microscope and what principle it is going to be work, as well as we'll see about the applications of this what we call transmission electron microscope. We'll see here. So first we'll see what actually Hall effect will give you. What actually Hall effect is going to be give us, and about the Hall effect we'll see. So then after what actually Hall effect is, with the help of Hall effect, what we can use, we'll see here. So Hall effect is used to measure the, otherwise is used to study the transport of charge in a material, that is in a material means like a metals or semiconductors. So in any metals or semiconductor sample, if it is present, then we can see how the charge is going to be transported in that metal or semiconductor. We are going to be see about that one, and as well as the if you see what is Hall effect is, when you keep a sample in a magnetic field. Okay, when you keep a sample in a magnetic field and some electric current is going to be passed through that sample, then what will happen we'll see here. So this uh, effect was observed by what we call scientist Hall in the year 1879. He observed this phenomenon. Okay, so he observed that when an electrical current passes through a sample which is placed in a magnetic field, a voltage proportional to the current and to the magnetic field is developed across the material in a direction perpendicular to the both the current and as well as the magnetic field. Okay, so this phenomenon is called it as what? Magnetic field. That means here what we are doing is we are taking a sample like a metal or semiconductor, whatever it may be. We are keeping in a magnetic field and we are passing electric current through that sample. By applying the electric field, we are passing electric current to that sample. So whenever if you pass the electric current to that sample, a voltage proportional to this current and the magnetic field is developed across the material in a direction perpendicular to both current as well as the magnetic field. So this phenomenon we will be calling it as what? Hall effect we are going to be called. Okay, this phenomenon is called it as Hall effect we are calling. And here the voltage whichever it is developed across that sample is called it as a Hall voltage we are calling. And this Hall effect has been leaded, like means it can be used in many practical applications, and as well as in the case of some magnetic field measurements, and to know the position motion of the charges also can be utilized. So this is what we have the Hall effect and Hall apparatus. If you take with the help of the Hall apparatus, we can be able to measure the what we call measure the charge sign of the charge carrier. That means we can determine the sign of the charge carrier actually whether it is positive or negative, which is present. We can determine, and as well as this Hall effect can be measures the continue. Hall effect can be used to measure the useful technique. For characterizing the what we call electrical transport properties of metals and as well as the semiconductors. Okay, mainly to characterize the electrical transport properties of any metal or semiconductor we can be used. Okay, so with the help of this, what we call how Hall voltage can be measured with the help of a Hall effect, we'll see here. Okay. So here, in order to measure this Hall effect, we will be considering a what we call we'll be measuring the Hall voltage. measurement of Hall voltage. Measurement of Hall voltage from Hall effect we'll see here. So for this purpose, we will take a sample here. This y-axis. In this direction, we have the x-axis, and in this direction, we have a z-axis. We will apply this. So on this, all the positive charges will accumulate here. Why these charges will accumulate, we'll discuss here. So here we apply here. Okay. So here in this figure, as it is shown that a material we have taken. So this is the material, a slab of material we have taken, and this slab of material is subjected to an electric field EX, okay, along the x-axis, and it is also subjected to the magnetic field along the z-axis as a HZ magnetic field is subjected along the z-axis. Okay, so due to this electric field, whichever we have applied onto this material, a current density Jx, okay, current density Jx will flow in the direction of Ex, okay, in the direction of flow, in the direction of Ex, it is going to be flow. So here, the current will be carried by the electron, which is having a charge of minus E. Okay, the current in this case is carried by an electron, which is having a charge of E. Okay, so when the external magnetic field Hz is applied perpendicular to the current here, so it will, whenever we apply this external magnetic field, which is perpendicular to the current, it will have a transverse magnetic deflecting force. It has a transverse magnetic deflecting force on this electron, which causes the flow of charge, flow of current. So transverse magnetic deflecting force will be there on the electron, so which causes the electron to drift down towards the lower edge of the specimen, which will drift down to the lower edge of the specimen. So as it is going towards the down lower edge of the specimen, so what will happen means the lower surface of the slab here, the lower surface of the slab here will be having negative charges. Otherwise, this slab will be collecting negative charges, and upper slab will be connecting the positive charges. That means majority of the charges on the upper surface will be positive, and you have the majority of the charges at the lower surfaces will be electrons you are going to be have. And also the excessive charges which are present in these surfaces. That means The excessive negative charges which are present in the lower surface, that is lower edge, and the excessive positive charges at the upper edge whichever present, they create transverse electric field EY. They create transverse electric field EY in this direction. They create the transverse electric field EY. Okay, so which is known as Hall electric field. We will be calling this transverse electric field EY, and known as the Hall electric field, which opposes the transverse drifting of these electrons. Okay, this will opposes the transverse drifting of the electron. So therefore, what will happen means here the equilibrium is going to be reached. So whenever the equilibrium is reached, in which the force due to the accumulation of the electrons become equals to the magnetic force. Okay, here the equilibrium is going to be attained. In this equilibrium, the force due to the accumulation of electrons becomes equal to the magnetic force, and so the flow of electrons will be stops. That means flow of electrons will be going to be stops here. So therefore, the net force on the electrons becomes zero. That means EY value is the net force on the electrons will become zero. That Fy will be equals to zero. We are going to. Now, if you consider so now here, if you consider the electric force on the electron is the electric force on the electron. The electric force on the electron is actually equals to minus Ey minus Ey. The net electric force on the electron is equals to minus Ey. And similarly, the net force due to the magnetic field is given by the net force due to the magnetic field. Due to the net force due to the magnetic field is E Vx Hx. Right. So the electric force on the electron is minus EVy, and the net force due to the magnetic field is E into Vx into H that you are going to be have. And if you consider the total force here, okay, the total force will be combination of electric force on the electron and the net force due to the magnetic force. That is total force. Total force, which is Fy, which will be equal to the combination of these two, that is minus Ey plus EVx Hx. EVx Hx we have. Okay. And we said that this total force is equal to zero. That is, the net force on the electron becomes zero. That means we can write this as minus Ey plus EVx Hx value should be equals to zero. Right. So this value is equal to zero. Therefore, this can be written as Ey is equals to Vx H x we can write. Sorry, Hz. No, this is Hz. Along the z direction, the magnetic field is acting, so it is Hz. So so if you take this E outside, so Ey becomes Vx that it is going to be have. So this EY, whichever we have here, this is the voltage. We'll be calling it as a Hall voltage. Is called it as a Hall voltage. It is called it as a Hall voltage. That means when we apply the magnetic field and the electric current is flowing through that sample, so there is going to be develop some Hall voltage across that one. That is EY, which is known as, we are getting it as a Vx into H. Okay. So from this, even we can calculate this, what we call Hall voltage also we can calculate from this. Hall voltage also we can calculate. The Hall voltage we have calculated already. So the Hall coefficient also we can calculate here. Hall coefficient. Hall coefficient we can calculate. So in order to calculate this Hall coefficient, we will be taking the electron density, that is the free electron density we are going to take in. So we will take let N be the free electron density. N be the free electron density we have taken. Then the current density Jx can be written as, minus of N E Vx we can write. Minus of N E Vx we can write. So from this we can write the Vx value as Vx is equals to minus Jx by Ne we can write. Vx is equals to minus Jx by Ne we can write. But already we have the value of Ey is equals to Vx Hz is there. Already we have the value Ey is equals to Vx into Hz we can write. Okay. So therefore Vx value we have got from this current density as minus Gx by Ne. So if we substitute here, we get Ey is equals to minus Jx into Hz by Ne we can write. Otherwise, in place of Vx, we can write minus Jx by Ne into Hz. Okay, so this we can write here. Ey is equals to minus Jx by Ne into Hz we can write. Therefore, Ey is equals to, we can write it as Rh into Jx into Hz we can write. Ey is equals to Rh into Jx into Hz we can write. Where Rh value is, this Rh value is equals to minus 1 by Ne we can call. Minus 1 by Ne. So this Rh is known as, the Hall coefficient for the substance. Rh is known as what? Hall coefficient we can call. Hall coefficient of the substance we can call. So this is what the Hall coefficient we can calculate. And also we can calculate the mobility mu value also we can calculate. Okay, what can calculate is we can calculate the mobility, which is represented with mu. Mobility also we can calculate. Here, mobility mu, okay, the mobility mu, which can be defined as the velocity acquired by the current carrying particle per unit electric field. So we can define it as velocity acquired velocity acquired by the current carrying particle. Okay, velocity acquired by the current carrying particle per unit electric field. Okay, per unit electric field. So mobility is nothing but velocity acquired by the current carrying particle per unit electric field we can calculate. So that mathematically can be given as mu x is equals to mu mobility mathematically we can given as mu is equals to Vx by Ex. Vx by Ex we can write. Okay. Mu is equals to Ex by Vx we can write here. So now already we have the Ey value. Ey value we can write in terms of mu. Ey is equals to mu into Ex. H that we can write. Okay. So because already we have the Ey value. Okay. Ey is equals to we have Vx into H. Okay. So we have Ey is equals to Vx into H. So therefore here from this Vx we can write as from this equation we can write Vx as mu into Ex we can write. So therefore here Ey can be written as mu Ex into H that we have. Okay. Right now we can write this value Ey is also equals to we know that Ey is equals to RH in terms of Hall coefficient. This is RH Jx Hz is there. So now these two equations are equal. So equating these two, so what you'll get is RH into Jx into Hz is equals to mu into Ex Hz. Okay. So therefore we can write RH is equals to mu Ex by Jx we can write. Otherwise, from this equation we can write R is equals to mu into 1 by sigma here. Okay, mu into 1 by sigma here we can write. Or simply we can write mu is equals to RH into sigma we can write. So here mu is nothing but the mobility, RH is nothing but the Hall coefficient, and sigma here it is the electrical conductivity. Sigma is the electrical conductivity. It is electrical conductivity of corresponding metal, whichever we have placed in the magnetic field. So these we can calculate. So that is, we have calculated the Hall voltage, we have calculated EY, that is Vx is equal to Hz we have got, and similarly we have calculated the Hall coefficient, that is RH is equal to minus 1 by Ne we have got, and similarly we have calculated the mobility mu we have calculated, that is RH into sigma we have got. Okay. Next we will go the experimental determination of the Hall voltage. Experimental determination of the Hall voltage. Here, the experimental determination of Hall voltage. Experimental determination of Hall voltage. Experimental determination of Hall voltage we'll see here. So in order to calculate the experimental determination of the Hall voltage, we will take a metallic strip which is having some small thickness and some length which is placed in a magnetic field. It is similar to this previous one only, but here we are going to be take the dimensions of the sample we are going to be consider, and we calculate the Hall voltage and another values. Here, in order to calculate the experimental determination of Hall voltage, we will be considering a metallic strip which is having some thickness in the order of millimeters, and it is having some length which is in the order of centimeters. We are going to be taken, and it is placed in the x direction, and the magnetic field is going to be applied in the z direction. So here we'll take this one. So these are the four magnetic field will be applied across these 2 points A, B. This is A, this is point B. So this is the south pole. This is the north pole of the magnet. And across these two, we are going to be measure the Hall voltage. Yes. Now across this, we will apply this what we call a electric field. So to measure the current, we'll apply a meter. There is a key to which where we have a rheostat. Based upon this rheostat, we'll apply the electric field. So this is rheostat we have. So this is the experimental arrangement. So we have taken, this is the sample, which is in the order of thickness, millimeters, and which is having some centimeters length. Right. So we are applying the electric field in the x direction and the magnetic field applied along this z direction we have applied. So now current is passed through this sample by using the rheostat. By adjusting the rheostat, we can able to pass the current through the sample to a suitable value by adjusting the rheostat between the points A and B. Okay, between the points A and B, that is two potential leads are connected to a potentiometer to measure the Hall voltage. Okay, so now between the A, B, two potential leads are connected to measure the Hall voltage, and across this CD, we are applying the what we call electric field, and we know that the Hall electric field which is given by Ey, which is equals to minus Jx Hz by Ne here. Ne here. Okay, Ne. Suppose here, if you consider the breadth of the sample is B here. This is the breadth of sample, and D is the thickness. D is the thickness of the sample. Okay, D is the thickness of the sample if you can take it. And say that I amount of current is flowing. I is the current flowing through the sample. Then we can calculate the current density. The current density is given by Jx, which is equals to I by BD. I by BD is the current density. Therefore, this value, if you substitute in this Hall voltage, if you substitute, okay, so you'll get Ey is equals to minus I by NEBD into, here we have HZ. HZ. EY is equals to I by NEBD into that you are going to be have. So from this value, we can get this EY into D is equals to VH, which is equals to minus I by NEB into HZ. So therefore, we can write this is equals to RH into IHZ by B, we can write. That means our voltage is equals to RH into I into HZ applied magnetic field by B. Okay. So this is the Hall voltage determination with the help of Hall experimental determination. Okay. So actually what importance you have with the help of Hall effect is, by the Hall effect, different measurements can be done, which follows like we can measure the value of Hall voltage. We can measure the unknown magnetic field also can be measured with the help of this. Even with the help of Hall effect, we can measure what we call this sign of the charge carriers. We can measure, and also the number of charge carriers per unit volume can also be calculated by using this Hall effect. And also we can decide whether the material, whichever it is given, whether it is a semiconductor or metal or insulator. So what type of material it is, whether it is a metal or semiconductor or insulator, can be found out with the help of this Hall effect. So this is the importance of the Hall effect is there. Okay. Next, we will see about the transmission electron microscope. Go for next one is transmission electron microscope, which is called it as a TEM. The transmission electron microscope, if you take this transmission electron microscope, is a very powerful tool which is used in material science. So mainly in the case of this transmission electron microscope, how it is going to work is a beam of electrons of high energy are passed through a sample. That is a very thin sample they are going to be passed. So when we pass this beam of electrons which are having high energy through this sample, these going to be make some interactions between these atoms. Okay, these electrons, means interaction between these electrons and as well as the atoms can be used to observe features like what we call the crystal structure, the grain boundaries, and as well as the atoms can be used to observe the features like what we call structural dislocations. Okay, so when the electrons of high energy is passed through the sample, the interaction between the electrons and atoms can be taken place, and this will be used to observe the features like the crystal structure, grain boundaries, and the features in the structures like dislocations. All these can be done with the help of this transmission electron microscope. Even it is used to study the growth of layers and as well as the composition and defects which are present in the semiconductors. Okay, so that means what type of composition is present in the given sample also can be found out with the help of this transmission electron microscope. Okay, and what call the defects which are present in the semiconductor also can be able to find out with the help of this step. So if you take the operation principle of this 10, that is transmission electron microscope, it mainly works on the principle as in the case of the light microscopes, which will work. Okay. But in the case of the light microscopes, they use light as which is going to be passed through the sample. But here in this case of this stem, we use the electrons to be transmitted through the sample. That is the difference you have in the case of the light microscope as well as the transmission electron microscope. Only the difference is there we consider light is going to be passed through the sample. Here we will be taking the beam of electrons which are going to be passed through the electron, which makes the interaction with the atoms of this material. Okay. So if you consider the wavelength of electrons, these are much smaller than the wavelength of light. Okay, the wavelength of electrons is much smaller than the wavelength of light. So which will leads to a good resolution of images, which can be attainable by the TEM, as which cannot be done in the case of the light microscope. Those things can be achievable in the case of this transmission electron microscope. Okay. So TEM is going to be give us the finest details of the internal structure. Okay, the finest details of the internal structure it is going to be give here. So if you see the TEM transmission electron microscope schematic representation of the TEM, if you see, right. So this is the schematic diagram of this transmission electron microscope. So initially we have the electron source. So the electrons are coming out of this source. Generally, you'll have the electron gun, which is going to be produce a stream of monochromatic electrons. That is a single wavelength electron. These monochromatic electrons stream is focused to a small coherent beam by the first and second condensing lenses. So these are the two condensing lenses we have, first and second condensing lens. So these two condensing lenses, what they'll do is they'll make a small coherent beam by the here. So after passing these electrons after passing through these two condenser lenses, the electron beam is passed to the condensed aperture here. Okay, this is a condensed aperture here. Through this aperture, it is going to be passed, in which high angle electrons are knocked off. The high angle electrons will be knocked off. The remaining electron beam now strikes the specimen here. The remaining electrons will be strikes at this point. So here, at this point, remaining electron, they are going to be right here. So from the specimen, the transmitted portion is focused by the objective lens here, by the objective lens into an image. Okay. After this, the objective aperture, which is going to be enhances the contrast by blocking out high-angled diffracted electrons. The selected area aperture here. Okay, the selected area aperture enables to examine the periodic diffraction of electrons by ordered arrangement of atoms in the sample. Okay, so after this function of the uh, what we call intermediate and projected lens here, finally we are able to the electron beam strikes the phosphorus screen and the images are formed at this point. So this is how the electrons are going to be passes through different lenses and specimen and through different aperture and intermediate lenses and project lenses. Finally, it is going to be give the picture on the phosphorus screen. Okay, in between the electrons, whichever are there, they will be knocked off. Finally, the image is going to be here at this point. So whenever the electron beam is interacting with the sample, so that is thin specimen interactions occur in the sample, those thin specimen interactions are used in the transmission electron microscope. So first, if you come here, you'll have the unscattered electrons. Unscattered electrons. So these unscattered electrons are actually the electrons are transmitted through a thin specimen, so without any interaction occurring inside the specimen. So the intensity of transmitted unscattered electrons is inversely proportional to the thickness of the specimen. Okay, the intensity of transmitted unscattered electron will be inversely proportional to the thickness of the specimen. So next you'll have another type of electrons which are elastically scattered electrons. So these electrons are scattered by atoms in the specimen without losing energy. Okay, without losing any energy, they are going to be scattered. These scattered electrons are then transmitted to the remaining parts of the specimen. Therefore, collecting the scattered electrons at different angles, you can get the information about the orientation, atomic arrangement, as well as the phase which are present in the atoms. Okay, and you have one more type of electrons, inelastically scattered electrons. Inelastically scattered electrons. Okay. So these electrons interact with the specimen atoms, with the specimen. So atoms in elastic manner. Okay. So these electrons interact with the specimen atoms in an inelastic manner. So by losing the energy, then they are transmitted to the remaining portions of the specimen. So the inelastic loss of energy is characteristic of the elements that have interacted with. So these energies are unique to bonding state of each element. Hence, these can be used to extract both the compositional and bonding information of the specimen. So in this manner, you are able to take the what we call information about the sample. Okay. So here in this case, if you see with the help of TEM, transmission electron microscope, what can we do is with the help of this transmission electron microscope, uh, we can get the morphology in the order of atomic diameters. In the order of atomic diameters, the size, shape, and as well as the arrangement of particles. Okay, arrangement of particles can be shown. So with the help of this TEM, we can able to find the morphology of the atoms, that is specimen of the sample. So the size of the sample, the shape of the sample, and the arrangement of the particles can be shown. Even you can able to find out the compositional information with the help of this TEM. Compositional information. Okay. So we can get the information of elements and as well as the compound are present in the sample and their relative ratios also we can find out with the help of this TEM. So this is one application of the TEM we have. Morphology also we can get, and as well as the we can get the crystallographic information. Okay. Crystallographic information. Can get the crystallographic information. That is the arrangement of atoms in the specimen and the degree of order, detection of atomic scale defects also can be known. So these are the application of the TEM we have. So these are the applications of the TEM which we have. And similarly, today we have seen about the Hall effect, Hall measurement, Hall voltage measurement, and as well as the how determination of the Hall voltage with the help of experimental also we have seen. And also we have seen about the TEM and the TEM, how we can calculate, means how, what is the principle which is involved in the TEM also we have seen. And what type of applications of the TEM we have, that is transmission electron microscope also we have seen.